Okay, everyone. So we're going to go over how to use LaserTRAMZ now. This will be the first part of the software where we're reducing the time resolved data in order to get the desired isotope ratios to calculate an age, which happens in the second part. If you didn't see the video on installation and you need help with that, go ahead and take a look at that first. So once you've got Spider open, go ahead and hit run. Okay, and in your browser, should pop up. Uh, should pop up this screen here. So it'll be blank initially, and you'll have this bar on the side with all of these widgets that allow you to control the program. So down here at the bottom, we have this box where we can input a file path. So go ahead and go to your LT ready file that comes out of the multi-filer, which was described in the prior video. And then copy is path, so you're just copying the path. If you don't have this bar enabled on your computer, you can come up here and just type path, and it'll pop this up, and you can copy it that way. On Windows, you just right click and its copy is, I'm not sure what it says, but something like that. Okay, so go ahead and paste that, click out of the box, then you can see we're loading. Okay, so looks like it loaded. We've got this table right here. So we're going to go to the top. So there's one sort of kind of bug here I haven't figured out. Go ahead and just pick an analysis and you'll get all the stuff to pop up. In this NAN, I can't get it to go away. So I apologize for that minor inconvenience, but there it is nonetheless. So we're going to go over all of these, everything that's here, and how to reduce ratios. So this upper left graph here has time resolved isotope ratios. The dashed lines with the large spacing are your background. The solid lines are your ablation interval. And then this dotted line is where you're projecting the regressions back to if you choose to correct for interelemental fractionation at the ablation site using regression. This was described by, I hope I don't butcher his name, but Jan Kostler, and then Patton et al. Wrote what I would consider a seminal paper on using exponential regression for this purpose. So this graph particularly, you can pan, just click and drag. You can scroll, so this will control X and Y. This will control X, this will control Y. And then you can reset. And then you can also save if you desire. You're probably going to collect a bunch of data where the uranium-lead ratios are similar across the board. So what you can do is you can come down here to this ratio plot ylim, and I'm just going to set this to 0.0. Let's do 4. Press enter, and anytime you reset, it'll come back to that now. It just reads that. Okay, so we have a uranium-lead ratio here, time resolved, and up here, this is actually for the 735. We're not going to go over that. Chances are, coming off the ICAP, you don't really care about that ratio anyway. So we can see we have our regression here, and that is just first order. Most people use the exponential regression. I would recommend that as well. So we're going to turn all these on to get to our exponential regression. And then one thing about curve fitting is you have to provide exponential regression curve fitters usually with a guess in order to converge onto the parameters you want. So in order to do that, just hit force exponential params, and there it is, it pops up. Okay, so we're just gonna move this ablation interval, just so you can see that moving around. Okay, should be able to see that. And then this ablation, projecting back to the start of analysis is kind of that's the theory, because at the top of the ablation site, before your first or at your first laser pulse, there's no downhole fractionation between uranium and lead occurring yet. So, in theory, you want to project back to the beginning of your ablation. In reality, most people just use wherever they select their first ablation, or wherever their ablation interval starts, be that due to ease of computation, or we all know that regressions have a confidence band that drastically increases outside the boundary of where you've actually regressed data. So your precision is going to be better if you just keep this set to your ablation slider. But if you want to honor the theory there, you want to set it to the start of the ablation. So up to you. I think most people in the literature just put it at the start of the ablation. So in the name of consistency, that's probably your best bet. Okay, so to turn on other isotope ratios, for instance, I'm going to turn on 3835, which obviously is going to be very large, something like 137.818. If it'll go there. Jesus. There it is. Okay. So there you go. You can turn on your other ratios again off the ICAP. You're probably only worried about 638. But it does help sometimes to look at the 7-6 ratio if you think there's some inhomogeneity. Um, that can help you out. Okay, I'm not going to describe what residuals are, but here are all the residuals for the regression. Ideally, these are normally distributed about 0, so about your best fit line. I personally really like using these to help me decide where I want my ablation interval when I'm selecting an interval. Things to look out for are funneling. So you get, funneling, so your residuals increase with higher values or lower values, usually higher values. What you really want to avoid are kind of curvature artifacts where you have a bunch of residuals down here and then up here you get a bunch of residuals and then it'll curve down. It'll, convex or concave, right? And basically what that means is that your regression is poorly describing the actual data. It means that you have a parameter or there's an extra regression parameter that's needed in order to appropriately approximate the data that you're regressing. This is one huge benefit of exponential regression. Typically, what you'll see in uranium lead analyses, I've noticed the more lead there is, the more this occurs, you'll get a distinct curvature. And the exponential regression handles that really well. Okay, so down here are all a bunch of statistics. If you want to use those, these are your standard errors at the intercept here in percent. These is for 735. You can see 735 regression stats. These are the 638 regression stats. So this may help you select ablation intervals as well. And then here are your R squareds. They're going to be fine. Okay. Uh, this is all time resolved data. So these are just your ablations. And these are intensities on the y-axis, and of course, time. This plot is also draggable, just like the one above. And you can do all the scrolling and all that good stuff. I typically use this in order to look at, you can really like zone in here and you'll be like, man, this ratio is changing in a very weird manner. It helps to come down here and actually see you've if you've drilled through your crystal or anything of that nature. Or if you fit an inclusion, you'll see that in 208 or 204. Okay. Also in this graph, you can change the y limit. You can put the intensities on a log scale, and you can turn on and off various analytes. This graph down here shows your confidence ellipse. on the ICAP, you're probably not going to worry about these too much, and it's just going to be collecting a lot of data in the background if you leave this on. So you may want to turn them off just in the name of speed of your computer. And the way you do that is you just uncheck generate ellipse. This data will be output in a different file, which you can upload into the second part of LaserTRAMZ, where it will correct the mass bias on your desired ratios. This is TW. This is Tara Wasserberg. The ellipse that's projected onto Tara Wasserberg. And then we have Wetherhill, if you want to visualize those. And then the alpha value associated with the confidence you can change here. I strongly recommend, if you want these confidence ellipsoids, to not change this. Basically, most software programs out there have this set to a 0.05 alpha value. And that doesn't change. That's just kind of the, I'm not going to get into it, but that's just kind of status quo, okay? So this means and regression, what this means is that all of your isotope ratios, except your uranium-lead ratios, are calculated using a mean and error of the time-resolved data, background-corrected time-resolved data. And then your uranium-lead ratios are reduced using the regression that I've described above. Okay, if you want to see how all that works in detail on that, there are some papers you should probably read. Horstwood et al., Community-Derived Standards, etc. Is the name of that paper. Go ahead and take a look at that. Okay, one last thing I need to go over here. So this array of dwell times here. So these are the dwell times that you set for each of these analytes in order from lowest mass to highest mass, okay? You're going to want to change those to whatever it is that you selected in order to make sure that those get applied. This is really only going to be important if you reduce the data using total counts, which that integrates the analytes and then takes the ratio. And then Poisson, I'm not going to go over. That's something that will be in review soon, if I can get my butt in gear. So I would not recommend using this. This is not peer reviewed. This is not very good for the ICAP. In my experience, and then in addition, other people that have used quadrupoles, including the element and other high-res mass specs, have found that the total counts approach does not work as good as the means and regression for various reasons. Tends to generate data that's more precise than it is accurate, or it'll be less concordant. Okay. So actually reducing the data, finally, what you want to do, let's say you're happy with this ablation interval, your cleaning pulses are not in your background interval, you've set your projected Y into or at your start of your ablation, you just hit approve interval. Okay, scroll down, there it is. So here's a bunch of ratios. I described these in the GitHub page, what they all mean, but there they are. Okay, so I'm just going to select a few of these and output the data so that you can see that, and we'll import that data into the second part. Hopefully I can speed up this video. Okay, so we've got a bunch of data reduced here, and you can see that in this output table here. So we're going to go ahead and export this, and the way you do that is you hit triple DT, um, and that will export the data. If you don't know what triple DT is, you just don't know. And here are the data files. Again, we're not going to worry about this ellipsoid data, but here is the file that you want in order to calculate ages. I strongly recommend that in this LaserTRAMZ folder, you find this output file and you either drag it to another folder where you want to store your data and archive it, and immediately change the name of this. Okay, so we're just going to say test output. And that is because if you go in and you reduce some data here and then you go to export data again, it's just going to overwrite that Excel file. Okay, that's all. And in the next video, we will reduce the ages.